fake data, which in many cases can look very real. So in this course, I'm sort of talking about later on, very, very briefly because of lack of time, about GANs. So you can actually generate sort of images, for instance, and many other things that look very, very real. So images that say people that don't exist, but the pictures look very, very real. You wouldn't know it's not a real person. Okay? And the list, as I mentioned earlier, goes on and on. Okay, so here are some examples and so on. So maybe I shouldn't go through these examples because they're so standard. So basically, we want the machine to learn its own. So the basic idea of machine learning is the old-fashioned way we do machine learning is basically we give the system code that tells it what to do. So you got clauses of if this happens, then you do that, and so on. So we really have to painstakingly know what the possibilities are and be very, very careful how we program things. But in some cases, it's sort of very time-consuming, maybe not very, very effective. So in machine learning, what it actually does is it sort of, we give it data, we give it the answer, in the case of supervised learning, or no answer, in the case of supervised, and the machine on its own learns how to do it. We don't actually have to program it step by step with you. Okay, so that's the essential idea of machine learning. So as I mentioned, supervised learning is we give it the right answer. Unsupervised data, we don't give the right answer, but the machine on its own classifies and find patterns and so on. Regression, we mentioned a minute ago, we have continuous functions, the outcome is continuous. So it could be critical temperatures that we have, superconductors, it could be sort of values that we have real estate, so the people want to sell property, we want to know how much it will cost in a few years and so on. Classification problem is we're actually, unlike continuous outcome, is a discrete outcome, binary or non-complicated. And actually one very, very common example, used also very commonly as a benchmark, is recognizing handwriting. So when you write, for instance, a number, you basically write a bunch of digits, of course. Each digit can be one of 10 possibilities. You classify what you actually write as one of 10 possibilities, from 0, 1, 2, 3, 4, up to, of course, 9. And one of the, and as I mentioned earlier, there are many, many facets to machine learning. And in particular, one recurring facet, a very, very important one, is that because we have such a large amount of data, we would like, if possible, to reduce the data into something more manageable. We can actually find patterns and be more efficient in what we actually do. Maybe also have insights in what's going on. So reducing the dimensionality of data is called dimensional reduction. And what I'm talking to you about today is basically one method, one very, very common method of doing that with no bias. You don't have any prior assumption what to look for. You just have the data, and the machine will generate for you the classification. I mean, it will generate for you, it will compress the data to something which is sort of doesn't involve as much data as originally. Okay. So I'll show you how to do it on images. I'll just sketch how it's not, of course, the images is one cartoon, but I'll give you a central idea of how it's actually performed in images and so on. You can apply for any data set in an unbiased way. Okay, so this is what I hope to cover. Of course, I'm not going to cover all this. But what I'll tell you about at the beginning is basically physical component analysis. So let me just review it very, very quickly. And this is what this slide, don't be, if you don't understand the slide, it's okay, because I'll come back to it at the end. And hopefully at the very, very end, the circle of ideas will close on itself and you'll be clear what this represents. But for now, I'll just give you an intuition of where I'm actually heading. So suppose you have an image of a dog or a cat or whatever it might be. The image can involve lots and lots of, a huge amount of data. If it's has lots of pixels and so on, if we have lots of images and each one has many pixels, it's a large amount of data. So we would like to compress that data, so reduce the dimensionality of that data to something smaller, without losing too much information. Okay, so that's the aim of dimensional reduction in this context. And how do we do that? So here on this vertical axis, you see that I have something called L. L is going to be corresponding to how many singular values we're going to keep. Okay. In this, what I've written here, I've basically eigenvalues for a symmetric matrix. But in general, we can think about singular values that we describe to what actually corresponds to, that we keep. And the point is, even though we have we might have a large image with many, many pixels and so on, in reality, this image right here is not a very, very bad image. You can sort of see it's a dog, you can sort of see, you can get its tail features. Similarly, this is a cat, and you can see what the cat is and so on. So this horizontal axis corresponds to how much data we actually keep. Okay,
so C corresponds to the image. Eh?
C corresponds to something we do with image. So the raw data corresponds to R. We're going to somehow do something with raw data. We're going to generate something which is associated with some covariance matrix. And with that covariance, which I'll describe to you later on, with that covariance matrix, its eigenvalues and eigenvectors will actually describe images. So if I have those two eigenvectors, I can decompose every new image into a relatively small number, because remember we have lots of pixels, but I'm going to keep only a small number, a small fraction of these pixels. And that will actually capture, nonetheless, the important features of the data. In this case, the image. But it could be anything. It could be audio signal, it could be anything. It could be a song that you want people to have and record it, and you want to put the data. So that would be the compressing data. It could be the video that people are taking, and you want to compress it to put it online, to be compressing. So that's basically it.
So in this cartoon, with L equal 1, the image is similar. We cannot distinguish where it's dot.
A disaster. We can't really say what's going on. And as I said, this is not really, I'm not giving you all the details here. The images themselves are always put at the bottom where the images are taken from and so on. So you can, of course, go to these websites and sort of read them in greater detail. But the core idea is that you have images. The images, you decompose them into these vectors. And it's enough to keep a small number of vectors to actually capture the image. Okay, so that's the idea. And these matrices for raw data don't have to be nice. They don't have to be square matrices. But these matrices will always be square matrices. And they're going to be symmetric matrices, and animation matrices, or actually Farlow matrices for when we have sort of not just symmetric matrices, which we can add up the Farlow transformations. So these have sort of nice eigenvectors, the square matrices, and I can decompose the image into these vectors. And as I'll describe to you later on, so you can see about the composition, but these vectors will actually correspond. This and similar ones will basically correspond to vectors we keep with this singular composition. So before I go on, this is of course a very, very general flavor. But before I go on, are there any questions? So the idea is you have lots of data, you want to compute the data. So an analogy that would be, for instance, if you have a vector in some number of dimensions, of course you can only draw with a limited capacity